Um, there's one other issue here, which is the Polaris issue. So people, I've gone back and forth with this on people. So I'll just say this. I believe that the tilt of the Earth was a modification to the model to explain the northern constellations. And I'll still maintain that it was Polaris, right? But it's hard to, I understand their point of view, right? So they're saying that Polaris was always 90 degrees north, right? And as they tilted the Earth, that also tilted Polaris 90 degrees to one side. But I would argue that they were seeing some constellations like Ursa Minor and Ursa Major too far south below the equator for this globe to make sense. And so what they did was they rotated upward so that those northern constellations, plus or minus Polaris, were now visible, or would be visible, because this is half of this is visible in the day, half of it's in the night. So they just tilted this thing so that when it's nighttime, the equator essentially rose up in the sky. And so I have a little kind of calculation for why I think they tilted it at that degree. And it has to go with the vertical field of view. So again, I feel like the eye is what was manipulated to get to these numbers. It's just too coincidental to me to not be. So I'll cover that a little bit later. And also people, well, how far do we see? I don't know. I don't know the true answer to how far we really see, because that assumes that I'm not seeing some kind of projection, that I am seeing a physical, actual thing in the sky to know how far it is, right? So the answer is I don't know. And does that make sense?
Yeah, of course it makes sense. If you don't know what it is, how the hell are you supposed to know how to measure it or how far it is?
Right. So I just go into a little bit about magnification here. And so what magnification means versus zoom. Okay. So when you look at it says magnification does not alter the perspective of the observer, right? You'll find that everywhere. But all that's meaning is that I'm not necessarily altering my height to something. I'm not altering the orthogonal lines necessarily, but I am altering the rate of these transversal lines when I am magnifying something by changing observer types. In other words, I go from one aperture to a different aperture. Or let's say it this way, I go from binoculars to a telescope, or I go from my eye to binoculars, right? That to me is magnification, where I'm now going to be able to resolve something more. Zoom is not the same. Zoom is like, I'm just taking this view, however much light this sensor can collect, and I'm just amplifying, I'm just kind of zooming my eye forward within that same view to see these transversal lines, which are going at the same rate, but maybe with a little bit more clarity. So it might be a subtle distinction, but to me, what it means.
I try and qualify that into real world terms. So if you take the picture on screen now, this middle top image, if you like, with the green and blue, and on your phone or your iPad, you screenshot it and then cut out that section and blow it up.
Right, and that's what I did.
You're calling zoom, correct?
Right.
Whereas if you were to actually have that image of whatever it is, so it's a load of boxes, but let's just pretend it's like a little tunnel. It's a real thing that we're looking at. And rather than looking at it with your eye, you pick up a magnifying glass, then you're going to physically increase the magnification. That's the word you used, magnification of it, and you can see more.
Well, yes and no with a magnifying glass, because a magnifying glass doesn't change the aperture necessarily. I'd have to think about that.
I realized that as I was saying it. Sorry. Yeah. So yeah, binoculars.
Right. Yeah. Move to a different observer system. Right. That's kind of what I'm saying with when I think of magnification. So, but the important thing, what the take home is from this is that when I zoom in on something, I'm not bringing something back that's gone. It was there. It was too small of a pixel maybe to see what was going on, but it's not getting brought back into view. Just so my point is that like when they say you can zoom in on boats that have disappeared off the horizon and bring them back. Well, in this definition, no, if they're gone, no matter what my zoom is. Now, if I magnify, if I move to a different observer system that has better resolution, a better theta, right, a smaller theta, then I would bring it back. Does that make sense?
Yeah. So in other words, the description doesn't make sense because people immediately just go out and pick up a single viewing system, a camera, one, and watch a boat go over the horizon. That's gone. It's never coming back. However, if you stand on the beach and watch a boat disappear over the horizon and then pick up a zoom camera, yes, you can bring it back until it disappears into that zoom camera. Then you can pick a telescope and bring it back.
Right.
And you're moving up in terms of scale, in terms of what you're viewing it with. But once it goes to the telescope, yeah, you might be able to use Hubble to do the same thing. But ultimately speaking, if that's the biggest thing you've got, it's gone.
Right. Yep. Once Hubble meets its, well, okay, well, whatever, if Hubble, you know, but once your telescope reaches its max, that's it. It doesn't bring things back. So anyway, it's the light collection ability of an observer. That's I guess the easiest way to put it. So if you don't change observer types, you're just zooming in. You're not resolving more. Even though it may seem like you're resolving more, you're just kind of blowing something up.
Yeah. So when Ranty's got his picture, let's say he had infinite resolution on the sensor of his camera, just for the sake of this example. When he's got the whole frame, i.e. he's not zoomed in, it's still got all the same information in that frame of that camera. It's all still there. But when he zooms in, he's just blowing it up. It's not like he's picked up a telescope and he's got more resolution to the image. Providing the pixels, it's all still in that image.
Right. In fact, you know, when you zoom in, right, your aperture is getting smaller. So anyway, the light that you collected is just specific to the observer, and when you zoom in, you're just blowing something up. That's the bottom line I was trying to make there.
Oh.
So let me just make sure there were no more points on part 3. Nope, that was it. All right. So part 4 was the one I kind of give to people as like hey, just take a look at this. I think I gave it to Jose and some other people. Like, why don't you just take a look at this, just to kind of, you know, see if there's reasons for, you know, alternative reasons, right?
You gave it to me, and this is the one that I had palpitations over when I was halfway through it. I was literally loving every minute of watching this because it was everything that I'd worked on the past year, and it was just like, oh, hello, this is it. This is what everyone should be looking into.
So this is kind of like this modeling out, I guess, of what an upward refraction would do. So here I model a this is what your perspective would look like if you were 6 feet above the water, right? And you rotate this rotates up and the ceiling rotates down. This is what your perspective would see, right? You would see the water line at your eye line, and you would see the sun like setting, right? That's I just kind of grossly modeled this one out, okay? But now I'm going to add in a vapor layer, right? Or a less dense layer, an emission refraction layer above the water line. And I'm in kind of within this layer as I'm viewing the world. And what ends up happening when I rotate this into perspective now is that you see an inferior mirage. And so I in my first video, I just kind of said, well, this is like, think of it like skipping stones off of a lake. And the ones that are beneath that are trying to get through this layer, they can't, and they skip away, and you don't ever see them. Instead, what you see is the ones that are skipping from above, inverted, and that's why you see this inferior mirage. So that was kind of the rudimentary explanation, but I thought it deserved a little bit more love, I guess. So so Wide Awake did some great boat footages, and Ranty, you've done some great ones too, of just boats moving off into the horizon, right, within these layers. And what you see is there's this inferior mirage zone or whatever beneath the boat, and as the boat gets further away, right, it just appears to get kind of swallowed up from bottom up within this layer. And so if you were to say, well, where's the true horizon line, right? Is it here? this yellow line in the middle? Is it over here? Where is it? Well, it's above all of them, right? And the only way you would know is if you had like a large object, like a sun, or let's say a distant mountain setting into your true horizon line. Well, then you could say, yep, okay, that's where the true horizon is, because the rest of this is just this less dense refractive layer that you're viewing the world in. Does that make sense? Here, let me model it for you real quick. So again, diagrams are, I guess, the best way to do some of this.
So yeah, it does make a lot of sense. It's just that you give us like a quarter of a second to answer. It's like,
oh, sorry.
Does that make sense? No answer. Right? Okay. It absolutely does make sense.
All right.
Yeah, I mean, I did this, and I put a load of stuff on my Google Drive about this. It was like different elevation heights on a boat, and you saw incrementally the boat getting hidden the lower you went down, and it was all due to perspective. Literally, I mean, I was able to document it and talked about it quite a lot on Nathan's. It was one of our favorite observations, actually.
Yeah, yeah. No, you've done some great like comparison stuff. It's really good. So let's model this vapor layer, I guess, and how when we rotate this thing. Let me go back to this slide real quick. So what's happening here is this is Snell's law, right? So here you have refraction, you have a critical angle being met, and you have reflection. And so as the you drop a normal line right here, perpendicular, and as this ray, let's take the bottom example here, as this ray gets more and more shallow, it's going to exit into this new medium, this less dense medium, right, at a shallower and shallower rate as well. Okay, and it's according to the refractive index of that medium. And so there's a certain point where I rotate this from more dense to less dense, right? So I'm going to rotate this thing upward, and there's a certain point where this angle, when it exits, is going to be 90 degrees to the normal line. Okay, that's called the critical angle. All right. Once that critical angle is met, any further rotation of this angle, any more shallowness to this angle, reflects that ray at the angle at which it entered. So the incident angle becomes the reflected angle. Does that make sense?
Inferior mirage, yeah.
Ah, that's perfect.
So wow. It has to be from a more dense to a less dense for it to occur in this direction, okay? Now, if you invert this, right, and now I have more dense up here and less dense here, so now this white area is more dense, this blue area is more dense, this green layer in between is less dense than both of them. You do the same thing, but inverted, okay?
Inferior mirage.
Right,
So,
and now you put these two together, okay? So this green layer is the same green layer here, and now I get a more dense, less dense, more dense phenomenon, and you get incident angle to reflected angle and incident angle to reflected angle. Okay, so far so good?
Yeah, Arwin would love this. This is his angle. This is his slant.
So now I'm going to rotate this angle up in perspective, right? I'm going to compress this to how it would be. So now this layer becomes like essentially like a triangle, I guess, whatever it is. And I've kind of modeled out the rays that are coming off the water that are supposed to come and hit your eye. They're getting reflected away. You don't see them. But instead, what you see are the rays coming off whatever's above. They hit this layer and reflect to your eye. So you see how this is kind of more pointing towards your eye. I tried to model it with the sun rays and the stuff coming off potentially the water. You can almost think of this layer as like a barrier, you know, or like a mirror. Whatever's beneath the mirror, you can't see through the mirror, right? But you're seeing whatever's above the mirror. How about that? Does that make sense?
Yeah, the obstruction that is the inferior mirage is above the water layer. It's actually in the atmosphere, but the cause of that is the very narrow viewing angle.
Yeah, essentially. This layer is emission. This is an emission refraction phenomenon. That's the argument. This is a upward refraction phenomenon taken to an extreme, where the ray, this upward refraction, right here, this ray being bent upward, is taken to an extreme, and it became a reflected ray. And this ray here, this is upward refraction in reverse, right? Because it's more dense to less dense. It's just happening in reverse, and it's getting reflected away from us. So we're not seeing the water anymore. We're seeing the reflected sky.
And this is happening at the horizon. So this would explain why you have it consistently across the entire horizon.
Right. So this is the boats. I put the boats in here now. So here's your boats, right, within this layer moving straight away from you along the water. But how you see it in perspective is they're going to move along the water. And then instead of keeping and moving off into your horizon, like in this version here, right, where the water line is at your horizon line, instead of that, they move into this weird, you know, inferior mirage zone. And they just start to move away and get swallowed up within this mirage zone. The further away they get, the more reflection off the bottom of the boat they're experiencing,
Yeah.
or reflected away, right? And the only thing you're seeing still is the top part of the boat, because that part maybe is experiencing a little bit less of a density change.
Yeah, so up until now, you've been detailing perspective in a neutral environment with no atmospheric effects. What you're actually talking about now is with the atmospheric effects, you know, this is what can happen. This is what the causes will be. So you'll have an mirage.
This is the light before it hits your eye now. This is what's happening before the light hits your eye. What was prior is what happens after the light hits your eye. How about that?
Yeah, so what you were detailing before, I like to call at the camera end. What you're detailing now is at the observation end.
Real world.
Yep. This is the effects of the light that's hitting your eye has gone through these contortions before it met your eye. And so you interpret those contortions. How about that?
Yeah.
And here I'm just kind of showing the skunk bay footage. So I'll just play it really quick. And I just take a water and I put a ruler in it because I was trying to like simulate Chris's building compression, you know? So I was heating up the water and cooling it down and doing all this stuff. But once I just remember seeing the skunk bay stuff. So I went back to it and just watched it again. And I was like, there's no way that I can look at that. I mean, how can you say that what's being cut off and what's not? Right? This is 12 hours worth. So how long do you sit out there and take a photo? Right? You know, Randy's been out there for a long time sometimes, but most people are going to sit there for, you know, 15, 20 minutes and, you know, and not be able to compare them like this. So I think these time lapses are awesome. Yeah. But what's cool is the building or the mountain in the back. It essentially it descends almost all the time. It doesn't loom up. You know.
Yeah, yeah. If you go back to that video again, sorry.
I don't know if I can replay this. It's kind of on a loop. Let me see. It might take a while to get there, but
yeah, it was basically the highest point. The trees on the right hand side. There's a pixel or two of change, literally just a pixel or two, but they don't move. But if you look at the bottom, you know, where it meets the water, you see an awful lot of change. And this is what we see. This is what I was trying to explain to you when I was looking at the buildings of Barrow, is that I'm not finding looming. So I have a post that's level with the top of those trees to the right, and it never changes in its position to the trees behind. But yet we get a lot of distortion at the water level.
Yeah, exactly. The higher you go, the less of effect you're seeing, right? The less of this rippling. You can almost look at this. It's almost like rippling of water, literally, right?
Yeah, you know, but it's not looming though. That's the thing.
Right. No, it's either going lower for the most part or staying where it is. So I just kind of do that here real quick. I'm like, okay, watch the ruler, watch the lines on the ruler as you just put your finger in water and ripple it across. And this may seem like a stupid thing to do, you know, but it's just kind of proving the point that what you're looking through is like this world, this rippling water world. So that's why I kind of put these little waves here. It's like you're just viewing the world as like compression, expansion, you know, over and over again with a predominant upward refraction, I guess, slant to it all. But it's usually just compression, expansion, and the object stays roughly at the same spot.
So let's just be clear. When you say upward refraction, you're not talking about looming. You're talking about downward compression, downward things being hidden down, not up. So yeah, it's the opposite. So when they say upward refraction, it's actually going down. It's hiding stuff. So right. So essentially, it would drop things beyond your field of view sooner than you would expect it to be.
Right. So your eye assumes straight lines, right?
Yeah. Yeah.
And so if something was bent upward before it reached your eye straightens that thing out, because we see the world in perspective, right? We see the world linearly.
So it would interpret it down.
Interprets it, it pushes, it unbends the ray to interpret that thing, you know, lower down. Now, downward refraction, right? That's the opposite. So if that occurs, now you're straightening out those lines, and you think it's higher than it really is. Okay.
So can you just explain what temperature gradients would need to be in play to create this upward refraction? Because you know, in my experience, that's all I've ever actually come across is upward refraction, which is higher. Right.
And that's exactly that's again, I encourage everybody to go watch John Dee's stuff, because this is all he talks about essentially. Is this upward refraction phenomenon over water, especially. So I don't know, Ranty, like the actual numbers of how much refraction is caused by what level of temperature difference. I just know that it seems to occur a lot more when there's a higher temperature gradient and the water is warmer than the air around it. So like when you're in wintertime, you're seeing a lot of these effects because the specific heat of water, the air gets really cold, right? But the water retains its heat for a lot longer. And so it depends on like time of day and things like that when you take some of these observations. But for the most part, there's an emission refraction going on where the layer above the surface of the water is a little bit warmer than the layers above it.
And yet when you look across a frozen lake, you can see for an awful long way. So this is the difference. What you're talking about is here that if you've got the water that's holding the heat, and you've got the colder air just above it, then you're going to get blockage sooner than you would expect.
Yeah, I'll kind of go through how that might play out here real quick. But just using Chris's footage, when he got the like 25 miles and barely any, you only started to see very little hints of building compression, like the floors getting smaller and bigger at like 25 miles worth. Otherwise, everything was almost exactly the right proportion, you know. But when that happened, the water temperature and the air temperature were exactly the same. He took it in early January in Miami, so your water temperature that day, I went and looked it up, it was 70 degrees and his air temperature was 70 degrees.
It's interesting that it's only been the past year or so that we've started talking about this compression issue. And, you know, I think everybody collaborating together like this, I mean, you've only put, what, 6 or 7 videos out? 6 videos? You know, it was literally a series. You put some of these videos out. You have the ability to actually decipher all this information and put it like you're doing right now, you know, that people can digest. And it's taken people like yourself, other people that may come into this debate in the next year or two, to actually progress this forward. But a year ago, we weren't talking about this stuff.
Right. No, and you know what? I know there's an argument like we don't need observations and things like that, right? And I would say that these are critical. Like if I didn't have like the stuff that you guys put together, there's no way. Like for instance, I was mentioning that Chris's tree line in the foreground. If I hadn't have found that, it was hard for me to standardize where the horizon line was. But because he had it in each one of his things, and he was taking them, you know, essentially from roughly the same observer height, it was like, okay, and now I can show that the greater the amount of refraction, the times when we see the most inversions and the most building compression and everything are the times when the horizon was brought lower versus the day when he shot the exceptional footage. And there was essentially no compression and no miraging and none of these effects, and the horizon was higher. So you couple that with the fact that these laser experiments seem to show laser bending upward almost always over water. And again, now you're at this, okay, optical density versus physical density. And whether or not, I haven't Googled optical density yet, but that's what we're seeing. We're seeing almost an inversion of physical density. And I don't know how high it goes. Someone asked me, well, this only occurs for like, 20 feet or 40 feet above the water. Well, almost all of these observations are within that zone, right? There's very few of these where we get above that kind of a layer. And I'm kind of theorizing now, or just kind of spitballing, is I don't know at what point the light starts to bend downward again. I don't know. I wonder maybe if optical density is inverse to physical density in a weird way. I mean, I'm just spitballing here. I don't know. And I wonder if upward refraction may be responsible in some ways for like our personal dome, right? How we view all these objects. I don't know. I'm just kind of throwing it out there, but.
Okay, well, let me change the subject very slightly right now. I'm going to do a promotion for your channel. So in the next 30 seconds or so, I'm going to put a few links in the side. So if everybody wants to click that link, go and subscribe over there. This is Travis on Life is Short. Subscribe to him. He's got all the videos up there. They reach into individual sections. You can watch them all. And I'm sure he's got a lot more stuff to come. So I'm going to spam the link right now. Jump over there, subscribe to him, then come back here and listen to the remainder of this. So I'm going to spam it right now. Here we go.
All right. Yeah. Thanks, Randy. I'm not like, I don't plan to be like a content creator necessarily, but I just kind of want to make sense of all this stuff. And so if I see something that I think is worthy of kind of putting together a little thing on, I'll certainly do that. I am going to put out one like kind of summary. I've kind of timed it here. I'm trying to get it down to less than 20 minutes of just kind of summarizing everything that we kind of talked about and putting some rules together, for I guess we'll call them perspective rules and things like that, and then kind of do a rudimentary calculator. But so pulling out these skunk bait images.
Well, hang on, before you carry on, just let people go over and subscribe, and then they've got to get back and they've got to listen to what you've got to say.
Okay, I gotcha.
So Nathan, I know you wanted to speak to Travis here. Is there anything that you'd want to ask him specifically?
No, I've got what I wanted, which is as he's going through his information, I've just got to, just get the clarity, because when you're watching it on a video, obviously you don't get the opportunity to say, can you stop and just say that again, because I didn't understand, which I have this time, which that's all I've wanted, and I've got that.
Yeah, it gets, again, that's why I kind of want to make the little rules of like breaking down this argument. So small, things get smaller with distance. Small things disappear, and small things or things get disappear with distance, and then just breaking down each one of those things and how they occur. So. And then as a caveat to all that, and then of course, light is getting bent all over the place before it even reaches your eye. So that's a bit of a factor. Are we ready to go again, or?
Yeah, sure. Yeah, carry on.
And I'm going to try to move. I know it's real late for you guys, so I'm going to try to get through this as quick as I can here. And I know it's been a long game for people, but
yeah, I just want to do a shout out to Return of Cat's Eyes. I hadn't actually realized I hadn't moderated this, so I feel guilty for that because I didn't think it was the real Cat's Eyes. So thank you. I've just modded you now. Right. Away you go.
So for the most part, there's a really kind of a clear image in one of these. It's like this one. And I kind of pulled it out from here where it's like just, you see a really good shoreline. And so when you compare the mountain height within that one, it's kind of fuzzy, but I zoomed it in and tried to find it. It's essentially the same height as when you got these lower refracted or these refracted wavelengths, and you can see further, right? And throughout the day, if anything, it essentially moved downward. It moved up a little bit here, but for the most part, it's moving downward throughout the day. So, and I also modeled out what the water line was doing throughout this whole, and the water line went a lot more, like it went crazy, right? It's way more up and down throughout the day. And you can see the lighthouse here, and it shrinks down to nothing and then expands back up again and shrinks. You can't see it here, so on. So that's just refraction, right? None of this is diffraction necessarily, because I'm not losing things. So let me put a caveat to this. So in a sense, it is diffraction because it shrunk down, right? It got down to a really small size. so in that sense, yes, it's diffraction, but it's more just this movement of water within a set diffraction field. I don't know how to explain that, but I just don't want to confuse the terms because it gets really messy. So I try to look at things in terms of the diffraction limit is kind of like my set in stone, vision of the world and where my horizon is. And then refraction, especially across water and things like that, is going to move this thing around before it reaches my eye. And I guess that's the best way to explain it.
Travis,
but I understand your point, Nathan, that yes, it's diffraction as well, but I just think it's hard to kind of separate the two sometimes. So,
sorry, Travis, can I just say that I've got a few people that have said in the chat that this is perhaps the best presentation they've ever seen. So, so it's a big thumbs up from my subscribers here now because they're all.
Thanks, I appreciate
it. Sorry. Oh, and also, Chris, you're still there.
Yes.
People that are saying, "Where's Red Pill gone? Where's he disappeared to?" You're still here. You're still listening, yeah?
Yeah. This is Travis's show, so he can. I'm just letting him do all the talking. This is his thing, so I'm just here watching.
And Travis, sorry, not Travis, Chris. Next time I bring you on, we are going to talk about some of the other stuff that you've put on your channel because it's definitely not all flat Earth, but it's definitely interesting.
Yeah, for sure, man.
Excellent. Right. Okay, Travis, away you go, mate.
Sure. So, so this is kind of these are John Dee's slides, right, where he's kind of showing the warmer, less dense layer and how it would affect a laser beam with cooler, denser air above. And he's done all his, laser experiments. And in this one here, someone was like, no, you see that thing, it's pointing downward. He actually got it all wrong. But what he's actually doing, if you read the caption, he's shining a laser from one side and he's shining a laser from another side. They're intersecting. And this scatter pattern here is what he's showing. These are the water droplets, essentially, of laser light kind of descending away from you. But this light is bending upward. And you can kind of see a little more clearly here in some of these examples. They kind of refract off into these angles. So he's done a ton of work on this stuff. And he has his slides are very kind of there's no words or anything. And that was kind of the reason I wanted to put words, because I like to listen to things like on the way to work and stuff. So I often put like the Nathan's show on, and I'll just kind of listen to things. There's not a lot I have to look at. And so unfortunately, Dr. John D, he just wanted to put these slides out, but they're very informative, but you have to kind of pause each one and read through all of it. So big plug for him, I guess. And again, if anyone can participate in his peer-to-peer thing up in the UK, that seems like a very worthwhile thing to do. So
I think it happened this evening.
Oh, did it?
Yeah, it went on tonight. I know that they were seeing the laser at a certain height, but then they weren't able to penetrate that cool layer, apparently. So maybe they should do it in a little, in climates where it's more equal, air temperature to water temperature. Yeah,
like I said, I mean, this is what you're looking at, right, with refraction. So it's like, and this is over 12 hours, right? So one-time shots on things are kind of hard, but what his observations have shown with however many, he says he's got 120 plus hours of telescope and laser light observations, is that it's almost always an upward refraction, an emission refraction phenomenon. So and it just bears out with all these other effects when you start putting two and two together, that's what we're looking through. The predominant refractive force, or whatever you want to call it, across water is an upward refraction. It explains building compression. It explains inferior mirages, and it explains the horizon getting dropped artificially. And so, so I do some time lapses here. I won't go through that. You guys can watch these on your own. But essentially, it's just the Chicago skyline and how much you can see of it. Look at Joshua Nowicki's channel. He's not a flat earther or anything of that nature, but he's just done some great time lapse work. So, and these time lapses are hard to get, right? It's a lot of man hours to sit your camera up and get a proper time lapse. So, anyway.
Yeah, that's the other thing. I don't think people understand. You know, people appreciate the work that goes into doing this kind of stuff. You know, it takes a lot to sit there for hours on end and do this kind of work day after day.
Yeah. So then I'm just kind of showing you how a constant upward refraction may look versus a more rapidly dissipating one. So I think when you have a rapidly dissipating one, you're getting a lot of bending at the lower aspects and you're getting less bending on the upper. And so when your eye straightens this out, it's pressing more information down into a smaller space. So I see my red line here, it's traveling more distance than this red line up here. And so what you end up doing is squashing this building down into a really small point. And so that's what I think is happening with Chris's lower floor building compression. And it's different, right? He has several different shots of it, and the floor is a little bit bigger the next day. Some days he saw 10 floors, some days he saw 8 floors, some days he saw 7 floors, and the rate within which they compressed was different. So I think it's like you're looking through these ripples of water, right? So kind of like this.
Well, yeah, I mean, there's a reason why I haven't put many videos out recently. It's like I've been there every day. And you're actually showing now essentially what I've been seeing. In fact, it's been worse than that. The inferior mirage that you're looking at now has been much deeper than that. So it starts higher up. So the blockage is more than what you're actually showing. And there's no point in putting videos out like that, because what's the point? What's the point in showing somebody a massive inferior mirage of blockage that says that if you took it literally, you would be living on a planet that was essentially probably 4,000 miles in circumference, you know, because the blockage is that severe.
Right, and that's the problem with taking all these optical effects as physical things, as physical, because now your radius of Earth just keeps changing, right? So when Chris has his observations out to 25 miles, okay, now the Earth has to be tremendously larger than it is, because there's essentially no loss. There's only 20 feet, 30 feet loss. So
yeah, now we live on Jupiter.
Right.
Yeah, now we live on Jupiter. But yeah, if you take Soundly's work, or you take the optical effects of the stuff that I'm seeing right now, we live on an Earth that's the size of the moon.
Yeah. Yeah. So you have to take account for all this stuff. So when you did this, I think we spoke about it earlier. I don't know, however long ago it was, but I thought this was pretty cool, and I kind of racked my brain over this for a while. But when you did a time lapse where you had the tide was out, right, and then the tide came in, and it was like 9:30 to 10:15, right?
Yep.
And so you had your camera at the same height the whole time. And so what I did was, and it didn't move. So I took your camera position and I just drew diagonals through the footage, right, to create the center of frame for your camera. It's not necessarily the horizon for your camera, because that would assume that you had it perfectly level, right? But let's say, but it is your center of frame, your center of view for your camera. And it's very close to where the horizon was, I think, in these photos, or in this video footage. So what I found was, and then you had a second video one day, and you just climbed in elevation because someone was questioning how high you were or something to that effect. I think they were actually questioning your height on the time lapse, right?
Yeah, I mean, the thing is, I mean, I don't think people really argue that anymore against me, because I'm so thorough with the work that I do. Literally, I've done measurements at every location that I ever do my filming from. Every time I've got a tape measure with me, I do a full 360. You know, I'm not bullshitting about my work, because I'm in it for the science. I'm in it for the truth. So, you know, originally when I first started doing this stuff, I had a very deep interaction with the Globers that were basically ripping my observations apart, because I hadn't done that. In the last year or so, I've tidied that up, and basically, you know, from now on, I've literally nailed it down. I've done it for the past year. I've shown where I am, my height above sea level, you know, the time, specified the time, location, there's everything there that they need. and I don't hide anything. You know, it's all there for people to take. And, you know, you've took this observation. Some people would say this is proof of globe curvature because it's blockage, but like what you're detailing here, you've taken it to another level, and you're explaining it as I've been explaining it for the past year, but you're detailing it in a you know, some kind of physical, you know, mathematics way.
Well, yeah, I try not to do too much of the math. I just want to show it like conceptually, but I just found this, like, I thought this was really cool. Maybe, I don't know if you guys think this is cool or not, but I thought this was really cool. So when you're at a 14-foot elevation, and you're at a 4-foot elevation, you're seeing the same thing. Okay.
Yep.
When you're at a 9-foot elevation and you're at a 4-foot elevation, a little bit later in the day as the tide came in, you're seeing the same thing. And then as the tide came in, you know, you're seeing the same thing that you saw at a 4-foot elevation that you saw at another 4-foot elevation. Does that make sense?
It does.
So what's essentially happening to me here is that you're viewing more refracted rays when the tide was out, right? Your floor, let's say, it could be just be by a few feet, doesn't matter, but your floor was not as compressed as it normally is. And so you're viewing more of these upwardly bent rays coming into your eye from this building far away, right? And so you're kind of bringing your horizon lower. So that's what this red line is, right? That's where this inferior mirage zone is in comparison to the center frame of your camera, okay? It's lower, right? The furthest point you can see. And as the tide rolled in, you started to see less and less of these upwardly refracted rays, and your horizon, your red line here is brought higher within your center of frame of your camera until here, where I think, you know, you might have been slightly pointed down, where the mirage zone is right at that point. So it makes sense. It just, all this stuff works, right? Anyway, does that make sense? I thought it was I thought it was cool. So
I think that's so cool, because up until now, I've demanded that Ranty accepts that this is only down to the limited angle. And I've explained earlier, it's like, I want to discount the refractive part till I understand that implicitly. Then I'll move on to refraction. Ranty's taken the opposite stance. This is only an atmospheric effect. This is just caused by a layer of dirty air. I know he's moved on beyond that simplistic explanation, but the reality is it's a combination of both, right?
Yeah, exactly. It is. I don't think you can't really separate these things out. So, because, you know, if you're viewing a small object, it's going to disappear. If you're viewing a bent ray, it's going to be moved within your field of view. Which chicken or the egg? It's really kind of hard in some of these cases. So, so what I kind of diagram here is that down here in this, I can't use my mouse anymore on this. All right. So, here's this kind, I just tilted, you know, Dr. John Dee's kind of photo here to show how this ray is coming to your eye now. Okay. And so here's your building up here, and here's your lower observer height. Now this is where Ranty is 4 feet off the surface. Okay. And he's receiving these bent rays coming in, okay, from this building that's a little bit higher.
Hang on, wait a minute. Why am I seeing these as bent rays? Is this because of the temperature giving upward refraction? Exactly.
Right. There's a warmer layer, optically less dense layer, lower down, and it gets more optically dense higher up. Okay. So these rays bend in this direction as they exit off this building and come down and meet that lower refracted layer. They bend upward to your eye. Okay.
Okay. So this is the norm, what you'd expect to see. What's the abnorm where you'd get to see looming, which I've never encountered right now? What would
these rays around? So these rays,
the temperature have to be above the water, and what would the water have to be?
Well, the air temperature would have to be, the water temperature would have to be colder than the air temperature, essentially.
Which is very...
And there's also a factor of pressure, though, but yes.
So how often do you reckon the water temperature is cooler than the air temperature above it?
I don't know the answer to that, to be honest with you. The only thing I can take is again, Dr. The amount of stuff that he's done over water, specifically over water, with observations and with lasers, and the fact that they just don't seem to bend downward at any point.
Yeah, I mean, I would agree with that, and I would say that probably, I mean, I've been filming there for the past year, so out of the, well, I've never, ever seen looming, ever.
Hold on, I just want to ask something. So, if you've got the air temperature on the top layer above the water at a higher temperature, then you're going to get upward refraction.
Downward.
No, sorry, downward refraction, which would make the thing look higher.
Right.
Anthony's got that once. In every one of his observations, he's never caught it apart from once. And it was under those exact circumstances on an extremely hot day.
Right. And I don't think I'm not arguing that it doesn't happen. I'm just saying that the predominant effect is upward refraction across water. And so here, take a look at this. So look at Ranty's lighthouse here. You see where it is in the center, according to, relative to the center of frame, right? You see how it's lower to the center of frame of, but it gets higher. Okay. But that's not looming. This object is brought higher, but it's not looming. It's just returning to baseline, right? Because it was lower originally. Does that make sense?
It makes sense to me.
It's not looming. Looming is when it's at baseline and it gets pushed higher.
That I've never ever seen this. This is what I've asked the Globers to try and provide for the past 2 years. I've asked them, find me proof of looming. Got to the point where I had to actually try and prove it or disprove it myself, and I've not been able to do that. Well, I've not been able to prove their point that looming actually happens. I can prove that we can see far further than the globe predicts, but I haven't been able to prove that it's through looming at all. It never happens. I've never seen this.
Yeah, I think if it does happen, it's rare and it's the exception, not the rule. I'll put it that way.
Yeah, it's definitely the exception. So in dozens and dozens and dozens of observations that Anthony did at the Isle of Man, one of them, he caught it literally where the land was up in the air. Weird, but it was just a really rare freak occurrence. Little did I know that it was actually what they classify in their 7/6R as downward refraction that's causing that. It's the polar opposite of, it's the inverse of what I thought it would be. Do you know what I mean?
Yeah.
What's also interesting is they've hijacked the terms, the two terms that we've just been talking about. We've got upward refraction and downward refraction. You'd think upward refraction would loom things up and downward refraction would lower things down, but they've got it the other way around. So where the norm is that it's normally upward refraction, that actually means that things get lower.
Right. Well, that's because your eye straightens it out.
Yeah,
right?
but what I'm saying is that if they're trying to do word salad, they will say, "Oh yeah, that's just upward refraction," and you think, "Oh, upward refraction, upward lifts things up," but that's not the case. Upward refraction means down. Right.
And someone, so I got to clarify this too, because someone like well, that's what's happening in your eye, stupid. But your camera doesn't do that. Your camera's not straightening anything out. So I was like, okay, well, where do I start with this one? So here's the bottom line to that. So if you were to look at let's say you had a coin in some water, right? In a cup of water, and you're looking at that coin, let's say at a bit of an angle, okay? Where are you going to view that coin?
Lower.
Well, no, it's going to actually appear higher, right? It's going to appear higher because you're going from less dense to more dense in that situation, okay? And so you're going to look at that water and you're going to be like, oh, the coin's right there. It's actually down and lower in the cup, okay? Because that is downward refraction. Does that make sense? You've brought it higher within but it's not there. Now, let's say that you now stick your iPhone in front of your face and you photograph that. What happens? Nothing happens, right? It's the same photo that your eye is seeing, okay? So that's not an argument. Your eye, both cameras and eyes assume straight lines.
Actually, I might do an experiment with this tomorrow. In fact, yes, I will do this tomorrow. I will get a pint glass and a pencil. I'll pour hot water into the glass. Then I'll put medium water in, then I'll put cold water in, and we'll see the difference that it makes as the pencil changes direction. because it will appear to change direction in the water.
Yeah, there's also weird things that go on though with when you're doing these water visual effects of water. Like let's say you're looking through glass as well. Now you got glass, air, and water. There can be some kind of trippy things that go on, and you have to kind of diagram out what's going on. But yeah, that's my point is that observers assume straight lines, cameras and eyes and everything. They assume however their cameras were built and whatever, but they view in perspective just like we view in perspective, right?
Yeah, you're sharing, Nathan. Yeah.
Yeah, can I just share this? It's only 30 seconds long. So Anthony was obviously watching the show, sent me the video I was referring to. He's even tagged it. Is this really looming? So if you can just bear with me for 30 seconds that this lasts, you'll see exactly what we're talking about as he pans right to the north end of the Isle of Man. So you'll see this. Might as well just sit in silence and watch unless you want to discuss it.
No, I think I've seen this about 1 million times.
I didn't get to watch it, Nathan. I'm sorry.
It's okay if you just click on my icon. It's this bit. Here we go.
There we go. Yeah.
Sorry, I switched back to another screen again. I'll watch it on the replay for sure, but.
I actually have a video of this with me thinking. In fact, it was the same day. I actually thought that I was seeing the Isle of Man from Bisbee, and I went out and I filmed, and I could see this wavy horizon, and I was sure it was land. Literally sure. I've got it on my. I've not even showed this to anybody, but it was exactly the same effect. Literally the same. So he's seeing this from St. Bees. I was seeing it from Bisbee.
Yeah, I mean, I think this is what's going on. I think this is this optical density issue, and I hope there's more numbers and data sets and stuff that come out from it. So we'll see. I don't know, and then maybe we get you can quantify like the temperature versus pressure and how much that's going to reflect the light in a certain direction. Because we have these data sets in many ways already, but I just don't. I think they've misinterpreted what's going on. I mean, that's the bottom line. So, or they reversed it essentially, assuming R, right? 7.6R. They've just assumed R is in there. So anyway, all right. This is Chris's floor example, real quick. So this is the lower floor building compression rate, right, within different days and different levels of compression and where the apparent water line was, and I kind of go through that a little bit.
So can I just ask here, do you think that there's a Fata Brumosa going on there?
So I look Fata Brumosa. That's the I only looked at Fata Brumosa. Fata Morgana is the inversions on inversions, right? But Brumosa is the that's the superior mirage, right?
Well, that's the water essentially repeating itself higher than it actually is. So it's basically copying the water underneath, like a Fata Brumosa of the water. Sorry, a Fata Morgana of the water.
Yeah, I don't know. I just think in terms of refraction at this point. But the Fata Morgana is the inversions on inversions. So it's like cold air, cold, warm, like almost like a ripple effect, and you get these like something's upright and then it's inverted and then it's upright again. That to me is a Fata Morgana.
Okay.
But again, I have to look into what they're defining as Brumosa and Morgana. I looked at it once and I just don't remember the details. I'm sorry. But I don't think that's what's occurring here. I just think this is upward refraction phenomenon. And you're pushing the visible world lower, right? Your horizon line is lower in this view. You're viewing more of the building as if you were higher.